Good morning to everybody. My name is Riccardo Zoccarato, and I am project engineer at the System Dynamics Competence Center of EnginSoft. Today I will talk about how to achieve multi-flexible body simulation by using RecurDyn powerful technology. Okay, so the agenda. I would start the presentation by giving you a brief introduction to RecurDyn and its nature. Then we will see how to build and simulate multi-flexible body systems in two different ways. So the reduced flex approach and then the full flex approach. After that, we will apply these two methods on a case study that is, the trailer that you can see here. And then finally, I will give an answer to all of your possible questions. So let's start with the webinar. And in order to introduce RecurDyn, I would say that it is a software for simulating the dynamics of rigid multi-body systems as many other tools available on the market, but with many more special capabilities. In fact, RecurDyn can simulate flexible bodies and also contacts between flexible bodies like no one else can, and this thanks to its unique technology. Also, it is faster than any other competitor because of its optimized solver. And then another interesting fact is that RecurDyn allows integrated particle simulation in order to simulate the coupled dynamics of a mechanical system with a granular flow or with a fluid like water or lubricating oil or other kind of fluids. In addition, RecurDyn is strongly customizable via Visual Basic or C# macros. Anyway, today I will focus on just one of these capabilities, that is flexible body simulation. This is, of course, required when the flexibility of a body affects the dynamics of a mechanical system. And so the body cannot be simply represented as a rigid body. Okay, then we start with the first approach for flexible modeling, that is RecurDyn reduced flex technology. This approach is used by almost every multi-body software on the market, and this approach is based on the Modal reduction method that is also known as Craig-Bampton method. This method starts from a finite element representation of the body, so a mesh, and then after a finite element pre-analysis, it produces a simplified linear representation of the actual structure response. And this is also called the super element. This simplified representation is mainly based on the vibrational properties of the body and also on the deformed shape of the body when some load is applied on the body itself. So practically, to perform this finite element pre-analysis, you need a finite element software or the RFlex generator that is integrated in RecurDyn. This method, I can say, is very fast in simulation, but it has some limitations due to the applied simplification, due to the linear simplification we have applied. Instead, this is the second kind of approach, that is the full flex technology. This particular approach allows RecurDyn to simulate every possible nonlinear flexible system. And so with this approach, RecurDyn doesn't perform any kind of simplification, but instead it keeps the finite element bodies in the multi-body environment. And so it can provide a true integration of the finite element calculation inside the dynamic analysis. Only some minor approximation are applied in the solver mathematics in order to improve the CPU efficiency. So finally, with this multi-flexible body simulation, we can analyze flexible bodies with nonlinear deformations, materials with nonlinear properties, and contacts over deformable surfaces. So every kind of possible system nonlinearity. Moreover, in the last release of RecurDyn, that is the V8 R5, RecurDyn has introduced a useful tool that helps a lot in managing the different representations of a body. And this tool is the G-modeling. This tool allows the automation of the process needed for converting a body from a rigid body to a full flex body, or to a reduced flex body. And so this is possible in particular with the automation of all the tasks listed here. So meshing operations, contact creation, finite element pre-analysis in the case of the RFlex bodies, and of course the conversion back to the rigid body version. Also, every feature previously created and applied to the body is preserved. So this means lots of joints, forces, and contacts that have not to be redefined. And so this way, no possible mistake is introduced in the model, and of course a final shorter modeling time is allowed. So this ends the theoretical part of the webinar, and now we can skip to the case study that I have prepared for the webinar. So as you can see, this is the case study, and it is a trailer with one single axle and supported by two lift springs suspensions. This system will only be loaded by gravity in our simulation. The shaft of the trailer is connected by a spherical joint to a fixed support, while the wheels are linked to the axle by revolute joints, and instead are linked to the ground by an in-plane joint. That is, in this case, it is simply a one-direction support. You can see in the section view a very simple kinematic scheme for the suspension. So each lift spring is composed mainly by two parts that are fixed to the axle in the midsection. So the upper part is also connected to the trailer by a revolute joint and a translational joint. We will model these lift springs with both the reduced flex and the full flex approach in order to compare finally the two flexible methods. Okay, first of all, I have used the G-modeling tool to convert the two rigid parts into RFlex bodies. So two simplified linear representation of the flexibility of the two parts are finally obtained. All the existing joints we have seen before, and that connect the bodies to the other part of the system are of course preserved, but I have to add some features to the model, and I would like to connect the lift spring upper part and the lower part, but I cannot apply a nonlinear contact between the two bodies to connect them. So I have to do I have to apply a simplification, and then I add two in-plane joints at the ends of the lower part. This in order to link the lower part to the upper part. With these two simple supports, then when the upper part will bend, so it will press on the lower part ends. Okay, after simulating the full flex model, we finally obtained these visual results, these three videos. So you can see that the trailer falls under the gravity load, and so the suspensions undergo a dynamic loading. You can see that the trailer, of course, oscillates many times, bending repeatedly and bending repeatedly the lift springs until the damping finally stops the oscillations. Also, you can see the blue vectors that are representing the joint loads applied by the lower part of the lift spring to the upper part. And then I have also plotted the von Mises equivalent stress on the deformed lift springs. Okay, so just skipping to the next slide. Don't know. Okay, now I think you can see it. So I have tested also the full flex approach on the same system. So with the G-modeling tool, I have converted the RFlex bodies into full flex bodies. So these are real finite element flexible bodies. This time there is no linear limitation to the model, so I can apply a nonlinear contact between the two parts. This is just one single contact that is linking the entire shared faces of the two bodies. Also, I have removed the fixed joint supporting the upper part of the lift spring, and instead I have applied a translational joint that allows the upper part of the lift spring to translate vertically and so press on the lower part. Okay, the next slide. So again, after running the simulation, we can obtain this visual result. The animation is, I can say, very similar to the previous one, so with the trailer oscillating a few times before stopping. Anyway, this time the system is very different because the two parts of the lift spring are interacting only through nonlinear contact. So the entire length of the bodies is loaded by a contact pressure. Okay. Just to have a comparison between the two applied methods and to understand deeply what have changed between the two model versions, let's analyze the suspension vertical stiffness in the two model versions. So this is a good way to compare the reduced flex and the full flex methods. So the stiffness of a flexible part is defined as the applied load divided by the obtained deflections. The global mass of trailer and freight is about 1,500 kilo. That would produce a static load of about 7.35 kilonewtons on each one of the two suspensions. During each of the two simulations, I have tracked the vertical displacement of the trailer center of mass and this is almost equal to the vertical deflections of the two lift springs. So you can see in blue, the blue curve, the deflections of the reduced flex lift springs, while in green the deflections of the full flex lift springs. The full flex final deflection is sensibly greater than the RFlex one, and this means that the RFlex lift springs are sensibly stiffer than the full flex ones, just about 19% stiffer than the full flex suspensions. And this, of course, is because the RFlex technology can only approximate the behavior of a nonlinear system, and this could lead to, for example, an underestimation of the system flexibility.